So after we apply 4 key simplifying assumptions, right, the idea that material properties are constant, that heat transfer only happens in one dimension, that the systems are in steady state, and that there's no thermal energy generation within any part of a thermal system, we took a look at how conduction occurs inside of planar and cylindrical objects, and we were able to figure out some key facts about what the temperature profile looks like no matter, what the temperatures at the boundary or whatever the, key values of the geometry are. We found some universal statements about what that temperature profile is by simplifying the heat equation using those assumptions and then solving for it based off of values of the temperature field at the boundary of those objects. And one of the very interesting things that we saw is that for both the planar and cylindrical systems, the heat transfer rate was proportional to the temperature difference between the boundaries of the object, okay? No matter if it was planar or cylindrical. So this leads to a very interesting point, which is that, is this kind of a universal fact of modeling heat transfer whenever we have those simplifying assumptions that we talked about before? So just as a reminder of what those simplifying assumptions are, all right, so the first assumption is that there's no thermal energy generation that's happening anywhere inside of our systems, all right? We also can assume that the material properties are constant. Material properties are constant. There we go. Which just means that the thermal conductivities and anything else, the radii and all of the things that are a function explicitly of the material, the geometry, don't change over time, all right? Or space or anything. We also assume that the system is in steady state, which means that nothing, including the temperatures and the heat transfer rates and the heat fluxes, nothing changes over time in our problems, all right? And last but not least, that heat transfer is happening exclusively in one dimension. Now, in cylindrical systems, we usually assume that that dimension is radial. In planar systems, we usually assume that that dimension is just, well, whatever, right? We just pick a specific direction over which we think the heat transfer is taking place, and then that's what we do. So these are the 4 assumptions that we make. And when we do that, we get that for all of the systems that we've seen so far, Q is proportional to delta T. So let's write down the expressions for the 3 different sorts of systems that we've seen so far so that we can keep track and know that that's the case. So consider the cylindrical system, which is the most recent one that we tried to develop and perhaps the most complex, right? So here, the expression that we had derived for the heat transfer rate was simply something that looked like this, minus 2 pi KL divided by logarithm R1 over R2 multiplied by a temperature difference. So this is what we had derived for the heat transfer rate. And notice, right, that I've written down this delta T, which without specifying, is this the inner temperature minus the outer temperature or the outer temperature minus the inner temperature. Ultimately, it won't really matter from the perspective of the fact that it will depend, right? So we know that heat transfer is occurring only in the radial direction, so we don't have to worry about too much whether or not the heat transfer is happening radially inward or radially outward, because we can always figure that out by explicitly determining what the temperatures are, okay? And so just one quick modification that I'm going to do is just to take this negative over here and then use logarithm rules to turn this into R2 over R1. Technically speaking, it doesn't really matter, again, because we don't really know what the sign of this delta T is. All right, so if you prefer, you can just think of us working with absolute values right now, right? Like we're only considering that the magnitude of the heat transfer rate is proportional to the magnitude of the temperature difference, right? So this is what we saw for cylindrical systems. Of course, we have a proportionality to delta T. For planar systems, we had seen the following, right? We had said that this was just minus K delta T divided by L times A, where A is this cross-sectional area of the wall. L, or pardon me, I should, to avoid confusion with the cell, let me write this as delta X. So this thickness, delta X, and this thermal conductivity K. So we have another commonality, which is the proportionality to delta T. All right? This negative also, once again, doesn't really matter because we can always flip how we define the delta T in this analysis, right? Like we can always just flip it and then absorb the negative into that. From the perspective of working with magnitudes, once again, it doesn't matter. What matters is that we're still seeing the same behavior. Last but not least, in the simplest case, and the first one we ever dealt with, we saw that Q is simply equal to H times delta T times the surface area over which the heat transfer takes place. All right, so the Q double prime in convective terms is just this heat transfer coefficient times delta T, where delta T is the difference in temperature between the surface of the object and the surrounding environment or whatever. And so we still have a proportionality to delta T. And so this leads to a very interesting question, or a very interesting idea, which is why even bother trying to figure out the solutions to the heat equation? Why bother working with temperature profiles in the first place? Maybe all I need to do is to know the value of the temperatures at specific points and to know the value of the heat transfer rates at specific points in order to be able to understand the behavior of the system without having to spend all this time like solving differential equations and finding values of boundary conditions, right? So, and you should know that if I had done this analysis for spheres, right? If I had tried to consider like spherical heat transfer, which I'm not really going to do in this course because not really that relevant, you would find the same idea. Obviously different expressions, but you'd still find that the Q is proportional to delta T. So, what is the idea? The idea is that for all of these systems, we can condense our understanding of them together by saying, well, what if we created a law that said, in plain terms, that the heat transfer rate has a linear relationship to delta T, and that the only thing that changes is this R, depending on what the geometry or the behavior of the system is. All right, like is conduction happening radially or is it happening in a planar system? Like what's the length of the wall? What is the thickness of the cylindrical section? All of those things get condensed into this R. And so this is exactly in line with the kind of methodology of heat transfer, where what we're trying to do always is set up a linear relationship between our parameters and then condense all of the complicated information into a constant, which is in this case this thing that we're calling R, right? And so this model, this idea of describing systems is the thermal resistance model, all right? So I'm going to write this down over here. This is the thermal resistance model. And the reason that this is called the thermal resistance model is because it behaves a little bit like how you might think of electrical circuits as behaving, right? In electrical circuits, we have this idea where we can relate the current, the electrical current that's happening through a circuit element, right? So a resistor or whatever. We can relate the current through that resistor to its electrical resistance and to the drop in the electrical voltage that happens between either end, right? So whenever you're trying to model electrical currents inside of a standard resistive element, we get this thing that is usually referred to as Ohm's law that relates electrical current, electrical resistance, and changes in electrical voltage. This is kind of the same idea. We think of the heat transfer rate as a thermal current, right? It's, in fact, kind of true, right? It's this movement of thermal energy in one dimension, under the assumptions we talked about, this movement of thermal energy inside of our system. That movement of thermal energy occurs as a result of a difference in temperatures in the same way that a current occurs as the result of a difference in voltages. And then how we relate that thermal current to that thermal voltage or temperature difference is via this experimentally derived parameter, which we can call a thermal resistance R. All right? And then all of the information about what the geometry of that given element is, all of the information about what its thermal conductivity, what the material properties are, all of that gets condensed into this R. And so you might tell yourself, oh, this is just us kind of creating arbitrarily this like little model because we look at what the electrical engineers and the physicists are doing when it comes to this, and then we say, okay, well, why don't we try to mimic them? But actually, it's a little deeper than that, right? Because think about it. We derived this expression. We derived it off of a bunch of very goofy, rickety assumptions, right? So I'm not necessarily saying I'm being the most rigorous person ever by getting to this. But we were able to derive it. And the question you have to ask yourself is, how do you think the physicists got this? How do you think electrical engineers got this? Right? It's by applying more or less the exact same assumptions when talking about the transport of electrical energy that we did when we were talking about the transport of thermal energy. So it's not so much that we are trying to mimic an equation that is like nice and dandy and is, derived from physical first principles just because we want to. It's that both of these equations are derived based off of relatively, ad hoc assumptions, right? And then all of the physics gets crammed into whatever the values of these resistances are. Okay? So if you were wondering where Ohm's law came from, you now know, right? It's just a bunch of linearizations and a bunch of simplifying assumptions about geometry. So now we have this thermal resistance model. So what do we do with it? Well, the nice thing about it is that we can take the analysis of complex systems and turn it into an analysis that is simple, at least from the perspective of those of you who have worked with circuits before. So before we get to that, let's just write down what these resistances are for the different systems that we've seen so far. Right. So to start off, we need to write down what is the resistance for a convective element, right? So I have, like I drew before, my wall in contact with some air. There's a heat transfer coefficient between these two things. What is the thermal resistance? Well, we can actually pull it from the expression that we had before. All we have to do is just divide, right? So we had written down previously that Q times R conv is equal to delta T, right? That's this equation. But then we had also said that Q was equal to H times AS times delta T, right? I guess I should just write A, where this is the heat transfer coefficient, this is the surface area over which the heat transfer takes place, and this is delta T, okay? When these things, because this is true, we can rewrite this. We can move this little portion of the expression over here and say, well, Q over HA is equal to delta T. And then by consequence, note that my convective thermal resistance has to be 1 over HA. All right? So if I want to think about it from an intuitive term, where I think of these thermal resistances as being basically a thing that tells me how much my system is resisting heat transfer through it, right? This thermal resistance tells me that it's inversely proportional to the heat transfer coefficient times the area. So if you want to maximize heat transfer through a system, you want to minimize the thermal resistance, which means that you want to try to maximize the surface area or the heat transfer coefficient. All right, and this is a super, super important engineering fact that we are going to talk about in detail later. All right, so This is what we get for convective resistances. Now let's talk about a planar system. All right, so we want to get something in the following form. And we had written down earlier in the lecture that Q was just equal to K times the area times delta T divided by delta X, where this delta X is just the thickness of the wall, okay? Once again, it's the same sort of deal. We want to isolate the delta T, and if we do that, the planar resistance that we wind up getting is just going to be delta X divided by K times A. So in planar systems, how do you try to maximize the amount of heat transfer? You minimize the thermal resistance. You minimize it by making the thickness of your planar element small, and you make the thermal conductivity and or the cross-sectional area of your planar element large, okay? And so it's really kind of nice to be able to concisely take all of the terms that involve the geometry and the material properties and combine them into a single thing, because we now have a relatively good understanding of how the material properties and the geometry alter the thing that we actually care about, which is the relationship between the heat transfer rate and the temperature differences. Now in the cylindrical case, the expression that we're going to get is a little stranger just because of the fact that we have all of that interesting geometry that we have to consider, right? So this is this. And then we had written down that Q was equal to 2 pi KL divided by the logarithm of R2 over R1 times the delta T. So what do we do? Again, just isolate. So the cylindrical resistance is just this logarithm of R2 over R1 divided by 2 pi KL. So in the cylindrical case, if we want to maximize heat transfer that's happening through the system, minimize the thermal resistance, so make the L larger. Why does making the L larger help? Because by making the L larger, you're making that like surface area, the surface area over which the heat transfer takes place, larger. So in the same way that it happens in the planar system, you would expect to get larger heat transfer rates for the same temperature difference. How R2 and R1 affect is not super obvious based on how this logarithm is described. But trust me when I tell you that if you make the cylindrical section thicker, that is to say, if you make R2 minus R1 larger, then this thermal resistance is also going to become larger. It's not a linear relationship, right? Because of the logarithm. But generally speaking, that thermal resistance will always go up when you make the thickness of this thing increase. All right? And so these are the expressions for the thermal resistances in these systems. So now that we have these expressions, why is it useful? Well, let's suppose that I had some complicated insulation on my house or something like that, and that I could model using those 4 standard assumptions that we keep using as just being kind of a composite planar system where maybe I have, I have a bunch of different layers of material. Maybe some of this is insulation, maybe some of this is glass, maybe some of this is brick, who cares? But the idea is that I might have some system where I just have a bunch of walls that have different thicknesses. And maybe I know the temperature in here, and I know the temperature out here, and I want to try to figure out, well, what's the temperature in here? So what's T2? And if I wanted to do this, I'd have to do a relatively complicated like energy balance or set of energy balances, or I'd have to solve the heat equation and try to figure out what the temperature profiles look like in order to be able to figure out what T2 is. But when we use the thermal resistance model, things become a lot simpler, because rather than modeling these things as like complete objects, where the planarity of them is required to be, for the analysis, we can actually just go in and say, well, forget this, all right? We can define a thermal resistance for each of these walls based off of their geometry and their material properties, right? Based off of the K, based off of their thicknesses, and based off of also the surface areas, or cross-sectional areas, I should say, right? Which we're, for the moment, just going to assume that they're the same, right? And if I have a situation like this, well, I don't actually have to think about the geometry in this way. I can just set this up as a thermal circuit where here's what I'm going to do. So this is my original image. What I'm going to do is I'm going to take each of these walls and treat them like they're a resistor in an electrical circuit, all right? So I'm going to draw a resistor with thermal resistance R1 that represents this wall, okay? And I'm going to say that the temperature on one side of this resistor is T1, and that the temperature on the other side of the resistor is T2. All right. And I'm going to do the exact same thing for the other two chunks of wall. So now, this second wall, I'm going to model as a resistance with thermal resistance R2 and with, a temperature on the right-hand side of T3, which I'm just going to name, right? And then you get the picture. Now notice that I've drawn all of them in series. That is, I've connected all of them one behind the other. And although intuitively it makes sense from the perspective of the drawing, right, the physical analogy that we're constructing, like the walls are one behind the other, so of course the resistances are one behind the other. But there's some physical meaning that comes from this, right? There's actually some important information that happens whenever you have thermal resistances that are set up in this way. And you may also ask yourself, when can we do this? When can we get away with doing this? And we can get away with doing this whenever we find that all of the heat transfer that's happening from one of these elements is going into the other elements. That is to say, suppose that I were to determine that there's a heat transfer rate Q in this direction over here. Does that heat transfer rate change within this element and this element? Does some of the heat escape? Well, we had assumed that the heat transfer was happening in one dimension, so it's not going to go anywhere else, right? We had also assumed that there's no thermal energy generation, so we can't add to the Q, right? The Q has to stay the same. And it has to stay the same here and here. It has to stay the same here and here, and it has to stay the same here and here, because there's nowhere else for it to go. And so whenever we observe that we have elements where this fact is true, where this physical observation is correct, we can always generate what's usually referred to as a series thermal circuit, okay? Which is just the resistances connected end to end. And this is super useful because for series resistances, the Q through all of the resistances is always the same. All right, so the temperature differences are not necessarily the same, right? Because the thermal resistances are not the same. But the Q always has to be the same. And the reason the Q always has to be the same, in addition to the physical argument that we made before, right? Which is that there's nowhere else for that Q to go, right? So this occurs, this heat transfer rate being constant occurs in series thermal circuits, right? And this is super useful because it lets us relate. So for example, if we know what T1 and T4 is, or let's suppose we know what T1 and T2 is, we can use that information with its thermal resistance to find what the Q is, and then that tells us the Q everywhere else. And so we can use this information to find properties of the rest of the thermal circuit, which is super neat. And so this is true whenever we have a series thermal resistance. Now, there's another potential situation, one which doesn't show up very often because it's not that physically reasonable, okay? So consider the following very fanciful setup, okay? Let's suppose that you have a wall, once again, so we're just dealing with planar systems, don't matter. And then, if we assume heat transfer is occurring in this direction, we have this wall which then splits into this kind of like this two-wall kind of deal, all right? And we're going to assume that there's insulation, all right, across the thing that's bridging these two materials together. So no heat transfer, approximately speaking, is occurring downwards or upwards, all right? And then these things then maybe combine like this. So you have a wall, the wall splits into two different materials. And this is the setup, okay? And if this is your setup, and let's say that we know T1, T2, T3, and T4, if we set it up this way, how can we convert this into a thermal circuit? Is it going to be in series? Not quite, right? Because the thing that happens is that if we know what the Q is over here, all right, we can certainly draw this as a thermal resistance, right? So that's fine and dandy. And we can say that the temperature over here is T1. And we can assume, for the purposes of this fanciful exercise, that the temperature on the left-hand side of both of these walls is T2. So we can still get away with this drawing, okay? And then we can also say that there's a heat transfer rate Q through this thing. But what happens over here? Well, through both of these materials, some portion of that heat transfer rate is going to be distributed, okay? So there's going to be a process via which this heat transfer rate splits into the top and bottom parts. So how does that happen? Well, let's not worry about that now. What we do have to worry about is the fact that the heat transfer rate is not conserved, right? That is at least in the sense that the heat transfer rate through here is not going to be Q, and the heat transfer rate through here is not going to be Q. What we do know, however, is that the heat transfer rate through here has to be Q, right? Because whenever this thing splits off, it has to come back together whenever it hits this fourth element, all right? So we can definitely write down that fourth element over here as the following. But what do we do with this and this? Well, these two chunks can be modeled as parallel resistances, all right? Two different branches, like the circuit branches off into two different pieces where some of the Q goes in one part and some of the Q goes in the other. From the perspective of modeling it in analogy to electrical systems, we would get something that looks like this. Where this, let's say, is resistance 2, and this is resistance 3. Now, these resistances behave just like every other resistance in the sense that the temperature on the left-hand side of this element is T2, on the right-hand side is T3, so we make the same assumption over here. And the same for this third resistance element, R3, right? The thing where it becomes complicated is trying to understand what that Q is, right? So now we're going to get this kind of Q2 and Q3 that's going to show up that we have to calculate using the rules of thermal resistances. So now that we've described these two different setups of ways that thermal resistances can be connected, all right? They can be connected in series or in parallel. How do we figure out things about these systems without necessarily having to worry about too much, like knowing everything in between? So for example, if I wanted to figure out what the relationship between T1 and T4 was, right? Could I find that without having to find T2 or T3? And the answer is yes, assuming you have enough information. And it has to do with some common rules that occur whenever you connect thermal resistances in series or in parallel. And they are directly the same as their electrical analogs. So if you already know a little bit about electrical circuits, then nothing that you should be seeing or will see here is surprising. So let's consider what happens when we analyze resistances in series. Okay? So in series, we just have a setup where we have some, arbitrary number of thermal resistances which are connected end to end. Let's say that we know T1, we don't know T2, we don't know T3, but we do know T4, and we know all of the resistances, right? In this scenario, can we figure out what the heat transfer rate is through the system without necessarily knowing what T2 or T3 are? And the answer is yes. And it has to do with the fact that Q is the same throughout this whole system. So keep this in mind, right? We had said that Q times R is equal to delta T. Now, we can write this a bunch of different ways. We can say that Q times R1 is equal to T1 minus T2 or T2 minus T1. Which one is which depends, again, on what assumption you make about which direction the heat transfer is occurring, right? If it's happening left to right, then this number is positive when T1 is larger than T2. So we're just going to operate under that assumption. I'm going to clarify it by writing down an arrow that tells me the Q is going left to right. So in order to make this equation work, because thermal resistances are always positive, this is what we're going to write down. Okay. So we have this expression, but then we also have this other expression. And we have this other expression for the same Q, because remember, the Q down here has to be the same. Same thing for R3. Okay? And so what's one of the interesting things that we can do here? Why don't we just add up the left-hand and right-hand side of all of these equations together and see what we get. And notice that in each of these terms, the middle temperatures, right, the T2 and the T3, show up, there's a negative and then a positive, and then there's a negative and there's a positive. So if we add up the right-hand side of all of these equations, the T2s and the T3s are going to cancel. These resistances are going to add up, right, because the Q is the same. And so ultimately what we're left with is something that says that Q times R1 plus R2 plus R3 is equal to T1 minus T4. And so the interesting thing about this little fact is that it now says, well, we have been able to relate the temperature difference between these two temperatures on either side of my thermal circuit to the heat transfer rate that's happening through it, plus this sum of the thermal resistances. And so from a pictorial perspective, what we have done is we've condensed the thermal circuit into an equivalent thermal circuit that consists of a single resistance, where one side of it is at temperature T1, one side of it is at temperature T4, and the thermal resistance of the actual thing is the sum of the thermal resistances that make up this composite equivalent thermal resistance. And so in series, the general rule is that for however large a chain of series resistances you have, you can always say that Q times this equivalent thermal resistance is equal to the difference in temperatures between either end of the system that you're considering, and then this equivalent thermal resistance is just the sum of the resistances inside of it. And notice that we use this to condense the entire thermal system, but this equation actually works for any little piece of this system, right? Like I can always say, well, maybe instead of trying to figure out what Q is as a function of T1 and T4 and these three resistances, why don't I instead make an equivalent resistance made up of these two initial elements, right, of R1 and R2? And in that scenario, I can absolutely say Q times R1 plus R2 is equal to the difference in temperatures at their boundaries, which is T1 minus T3. All right? And so I can do this with any little chunk of my series thermal resistance. All right? Now, this is what we can do for series thermal resistances. What about for parallel thermal resistances? And these are, again, a little bit more annoying. Parallel. So we have this scenario. We have this scenario where, my thermal circuit branches off in half with these parallel thermal resistances. Let's say this is R1, say this is R2, R3, R4. Let's assume that there's a Q coming in through here, which splits off into a Q2 and a Q3, and then combines back again into a Q, all right? And this is temperature T1, this is temperature T2, this is T3, and this is T4. All right, so how do we find not just what, it's like suppose that we wanted to find what, I don't know, T2, T3, and its relationship to Q was as a function of these two thermal resistances or anything else in the system, right? Let's consider trying to do an analysis. Well, the first thing that we want to do is to try to simplify it. And one way that we can simplify it is by trying to combine these two parallel resistances into a single one, into an equivalent resistance. And then this becomes like a nice normal, series thermal circuit. How would we do that? Well, notice, right, that for both of these resistances, the temperature difference is the same. All right, so Q times R is equal to delta T applies for both of these thermal resistances, except that now the Q's are different, but the temperature difference is the same. Okay, so this is T2 minus T3. And this is also T2 minus T3, except that now, right, we're using different Q's. And so we can always ask ourselves, well, what is the Q that is happening through each branch? Well, we can find it, right? Assuming that we know the temperature differences, assuming that we know the resistances, we can immediately find what that is, right? And so we can see how it splits. As long as we know information about the temperature differences and about the resistances, we can see how these things wind up splitting. Okay? We also, by the way, have to say that these two things are true, but what we are trying to find is an equivalent resistance that we can plop in here, right? So some equivalent thermal resistance that replaces these two things such that Q times R equivalent is equal to delta T, which is in this case T2 minus T3. And this is the whole Q, right? Because the thing that's going to be going through this equivalent thermal resistance is the whole Q. So we have these three equations. Is this enough to be able to get us to where we want to go to develop this thermal resistance? Almost. There's another key factor that we have to mention, another equation we have to write down here, which is that the sum of those two heat transfer rates, the sum of the two thermal currents going through each branch of this thermal circuit, has to be equal to Q. All right? So this is very convenient because we can write this down as a function of T2 minus T3 and the resistances, right? We can rewrite this expression and then plug it in over here to see if we can't solve for the equivalent resistance. All right, we're going to get something that's kind of nasty, but it'll work out fine. So what do we get? Well, we wind up finding that Q is just equal to Q2, which is T2 minus T3, divided by R2 plus T2 minus T3 divided by R3, right? So that's this plugging in the two expressions that I had before. I can, of course, combine this into two terms, or pardon me, into a single term. Because I can just say, well, this is just T2 minus T3 multiplied by 1 over R2 plus 1 over R3. Okay? It's the same expression, I just factored out the delta T. And then I can say, oh, well, this Q is just equal to T2 minus T3, right, divided by the equivalent thermal resistance. And maybe I'll write this a little bit closer so that you can actually see it. T2 minus T3 divided by the equivalent thermal resistance. Okay? What's the beauty of this? The delta T's cancel, right? So I can just divide by delta T on both sides of the equation and obtain that 1 over the equivalent thermal resistance is the sum of 1 over the individual resistances, right? So the inverses add. It's kind of a weird idea, but we've derived, right, that for parallel thermal resistances, the inverse of the equivalent thermal resistance we get in the system is just the sum of the inverse of each of these thermal resistances over here. The sum of the inverses. And so this rule applies for any number of parallel thermal resistance that we might consider. And so in general, for parallel thermal circuits, if we want to create this equivalent, thermal network or this equivalent thermal resistance, we have to state that the equivalent thermal resistance, or the inverse of the equivalent thermal resistance, is the sum of the inverse of all of the individual resistances. And one of the really interesting things about this is that because of this inverse property, the parallelization makes it such that the equivalent thermal resistance is always equal or smaller to the resistances of each of the little parallel components. All right, so in series thermal resistances, the equivalent thermal resistance was always larger than the individual pieces of stuff inside of my thermal circuit because we're adding them all up, right? The thermal resistances get added up. The fact that we're doing inverses here, that we're adding inverses, means that the equivalent thermal resistance in parallel circuits is actually smaller than the thermal resistance of the individual components, right? And that also tells you something about how you want to set up composite thermal systems if you want to maximize or minimize heat transfer. If you want to minimize heat transfer, set them up in series. If you want to maximize heat transfer, set them up in parallel, right? Give the heat more different ways to be transported through your system, right? And so now that we've figured out what these rules are, right, this idea of how to model composite, complicated systems that involve heat transfer as these simplified thermal circuits, now we actually have to get our hands dirty and work on some examples where we can take these sorts of systems, put numbers on them, and then find other numbers by plugging and chugging. And that's what we will do in the next lecture.